Hello students, welcome back. Okay, we are moving on to the third part of the solar flux module. This is going to be about elevation and azimuth of the sun. I mean, over the course of the day, if you had kind of a picture showing like where the sun was at different times of the day, like what I have here in the background here, there's two different values that we're going to be able to compute at the end of this lecture. One is the elevation angle, that's how high above the horizon the sun is at any given time and at any given location. So your elevation angle will depend on, well, it'll also depend on the date, which is part of the time, I suppose, and also the location at which you are on Earth. We're also going to be computing the azimuth angle. What is the heading of the sun at this time with respect to north? What angle do you turn to? That's the azimuth. And then the elevation is what angle above the surface of the Earth that is. You're going to be able to compute both of those at the end of this lecture. So we can describe the location of any of any object or whatever in the sky in terms of its elevation and its azimuth. Now, its azimuth is going to be the heading with respect to north. So like if north, in my case sitting here in my living room, that way is north. So azimuth is how many degrees I turn clockwise from north to be in the direction the object is. So it is the heading with respect to north, and we'll get to that in the second half of this lecture. But first we're going to be talking about elevation, which is the angle it is above the horizon. As long as you have an azimuth angle and an elevation angle, you can always describe the location of any object in the sky. So we're going to be working with both of these. Now, in practice, meteorologists in general only care about elevation. If you're talking about, like, here's a square meter of the surface of the Earth, what is the flux of radiation on that square meter of the surface? It doesn't really matter whether those rays of sunlight are coming from the west or from the east. It's how high above the horizon they are that matters. So meteorologists almost never take azimuth into consideration, but for the purposes of energy, we're of course going to be caring about both because we're going to have the orientation of a panel. Okay, is it facing a little bit to the south? Is it facing a little east, a little west, or whatever? The orientation, where is the sun in the sky with respect to how is our panel positioned will in fact matter in the context of this course. So this local elevation angle, which is the right term for our sun angle or whatever, the local elevation angle, is called psi. And it is the distance, how high above the horizon the sun is at any given time. Obviously it varies hugely over the course of the day, from right on the horizon at sunrise and sunset to some angle above this horizon at local noon. Excuse me. This local elevation angle, psi, of the sun is going to be something that we're going to be able to compute using an equation that's a couple slides away. Excuse me, I have a tickle in my throat. And it's going to have a number of terms in it that depend on the local latitude. Now the symbol that we're going to use for latitude is going to be phi. The local longitude, which is going to be lambda e. I don't know why lambda e, but that is just what the book I was used, so we're going to stick with that. It's going to depend on the solar declination on any given day, the latitude at which the sun is directly overhead at noon. And that, of course, in and of itself depends on the day of the year. Okay, and then we're also going to need to know the local time, which I'll use TUTC as my symbol here because we're going to do it in terms of Greenwich Mean Time. So it isn't like our time is going to be, I don't know, 12 when it's noon or something like that. It's going to be expressed in terms of Greenwich Mean Time, like what you learned about in the last module. And here's that horrifying looking equation that is what we're going to be using here. It's got all kinds of sines and cosines. It's got sines and cosines, well, it's got sines on both sides of the equation, and oh my goodness, what a mess. But it's not actually so bad. I mean, notice though your overall strategy here is, if we're trying to solve for psi, and psi is all by itself on the left-hand side, but it's inside of a sine, what we're going to have to do is solve for the right-hand side of this equation, and then take the inverse sine of that in order to solve for psi. This TD here is a symbol that we hadn't seen before. That's going to be the length of a day, and it's going to be in the same units you're using for your time in UTC. If you're expressing time in units of hours, then, we're like, your current time is 4, and that means you're at like 4 UTC, or 4.5, which means you're at 4:30, then your TD will be 24 hours. If you're expressing it in some other units, like if you're talking about how many seconds into the day it is at Greenwich Mean Time, then you're going to use seconds for your length of day. However you need to do it, just as long as the units all work out. So let's see here, you'll have it at any given time in TUTC, in the red box there. You're going to be able to solve for your local elevation angle at that time, as long as you know your latitude and your longitude and your solar declination and all that kind of stuff. Alright, I mean, it's ugly. What looking equation, but it can certainly be done, okay? It's not the end of the world. And actually, you can use the algebra and rearrange this to solve for the time UTC in which any particular solar elevation angle occurs. It's a mess, but it's the equation that I have there in that red dashed box. And that is, you're finding the time at which any particular local elevation angle, psi, is occurring. This is pretty neat because you could do things like figure out the times of sunrise and sunset. Which actually that would be the time at which the local elevation angle is 0, right? Well, it actually turns out to be a little bit more complicated than that, because it turns out there's lots of different ways to define sunrise and sunset. For example, there's geometric sunrise and sunset. Geometric sunrise and sunset is when the center of the sun just breaks the horizon. Okay, there already is half of the disk of the sun above the horizon, or already half of the disk below the horizon, depending on how you want to think about it. That's called geometric sunrise and sunset, and that is going to be the time when psi is actually equal to 0. Okay, so you could actually plug in here, when do I mean psi is equal to 0, plug 0 in for psi, go enter all your solar declination, your latitude, and your local, your longitude, and all that kind of good stuff, and you'll solve for the time in UTC in which you get geometric sunrise and geometric sunset. How about apparent sunrise and sunset? Apparent sunrise and sunset is defined as when the disk of the sun just breaks the horizon. Well, the sun is a finite size. There is actually some matter of minutes between, or at least seconds, between when the top of the disk of the sun breaks the horizon versus when the middle of the disk of the sun breaks the horizon. And you can solve for apparent sunrise and sunset using this equation by just using the values of psi when psi is equal to negative 0.833 degrees. The center of the sun is about 1 degree below the horizon when the top of the sun breaks the horizon. So you could solve for the times of apparent sunrise and sunset. And in fact, you could solve for any of several other ways of defining sunrise and sunset and so on. For example, civil twilight happens when psi is equal to negative 6, when the center of the sun is 6 degrees above and 6 degrees below the sunrise and sunset. Civil twilight has to do, it's an aviation term. It has to do with certain kinds of flight operations happen. Military twilight happens when psi is equal to negative 12 degrees. Astronomical twilight, it has to do when psi is equal to negative 18 degrees. These are just different ways of defining dusk and twilight and so on. And using this nifty equation, we could do any of those things. Let's just focus for a moment here on geometric sunrise and sunset, because we're not really going to care about the amount of power that our solar panel can produce when the sun's not even above the horizon. I mean, yes, you can still see enough, even though the sun has already set, for another hour or so, you can still see enough to, like, go play basketball out in the driveway, because it's twilight. It isn't yet astronomical twilight when it's dark enough to see stars and all that kind of stuff, but it is not enough to be producing a meaningful amount of solar power. So realistically, for the amount of solar power we're going to be generating, or the amount of heating of the surface of the Earth, to think of it from a meteorological perspective, we're going to need to be able to compute geometric sunrise and geometric sunset. So let's try that. Let's actually do an example here where we're going to compute geometric sunrise and geometric sunset on, let's just say, September 10th in Evansville, Indiana, where I live. And there's the latitude and longitude of Evansville, Indiana. All right, I gave it to you in degrees there, but the problem is actually going to need it in radians. So we're going to actually compute the radians here in terms of, the latitude becomes 0.66 radians, and the longitude becomes negative 1.5 radians. As I'm seeing that, I'm remembering, I think there might be a trick here. Maybe we'd have to check this here. It might be that it's positive, that many radians. Normally in meteorology, we use the western hemisphere as being negative longitudes, and the eastern hemisphere being positive, but if I remember right, it's for some reason the other way around in this equation. Before we get to project 1, I'll have that all worked out for you, and you'll have a handout or whatever as to why there's a difference for that matter. But just for the purposes of making this work out, I know I did it once already, so we'll figure out. What is the geometric sunrise and sunset on September 10th? Well, okay, to get geometric sunrise and geometric sunset, you're going to need to be finding the time in which that sun angle, that solar elevation is 0 degrees. And September 10th works out to Julian day 256. So if I first need to figure out my solar declination, because the solar declination delta S is all over the place in that local elevation angle equation, we get local elevation, solar declination is equal to phi r times the cosine of all that good stuff there. And if we plug in that TR is 173 degrees, that's the Julian date of the June solstice, and T is 256, that's the Julian date of September 10th. C is 2 pi. P is equal to the period of the Earth's orbit, which is 365.25 days. Phi r is the tilt of the Earth's axis, which is 23.5 degrees roughly, 23.45 degrees to be strictly correct. You get that the solar declination on this day is 4.53 degrees north, which there I have it converted to radians. Now, when I was doing this, I do not move forward until I know if that's right. So I wanted to figure out if that is right. I'm going to go to something like wolframalpha.com, or I use my analemma or whatever, and I'm going to look this up before I'm just Googling what is the solar declination on September 10th will give you an answer. Okay, you're not going to get exactly the same answer because obviously the solar declination varies a little bit based on like whether or not it's a leap year and stuff like that, but you'll get a close answer, okay? Alright, so part of the answer that we need is that the solar declination is this many radians. Now we're going to plug that into our equation that tells us the time in UTC at which a given solar elevation angle happens. We plug in here that phi is equal to, psi is equal to 0. That is the angle we're looking for. TD, remember, is 24 hours, just to remind you of a few of these constants here and so on. Well, there's a plus or minus there. And that plus or minus is the trick here. We need to, you can see we actually end up with two answers. You end up with a solution that TUTC is equal to 11.6 hours, and you get TUTC is equal to 0.07 hours. What does this mean? And again, remember, there is this goofiness, see that lambda e there, that is the longitude. I'm remembering now. That longitude had to be positive in the Western Hemisphere and negative in the Eastern Hemisphere for these answers to work. But we will get that all figured out. Okay, so now this top solution here was the one in which we took that plus or minus in the equation and we interpreted it to mean plus, and that will give you the time of sunrise. Okay, the plus gives you the time of sunrise, the negative gives you the time of sunset. So when you interpret this as a negative sign there, the plus or minus becomes a negative sign, that'll give you the time in UTC of sunset. Now what do these numbers mean? 11.6 hours means that it is 11 hours plus 0.6 hours. Okay, 11 hours plus 0.6 of 60 minutes is 11 hours and 36 minutes. So this is at 11:36 UTC is when the sun rises in Evansville on September 10th. And in the same sort of way, so okay, I gave my time is 11:36 UTC. In the same sort of way, if I, there we go, if I show you that the sunset is at 0.07 hours, that means we are at 0 hours plus 0.07 times 60 minutes, right? Because if that gives us our time, which is 0004 UTC, 4 minutes after 0 UTC. All right, we can convert that to local time in Evansville. Evansville is in Central Time, which is 5 hours behind UTC in daylight savings time. So 11:36 UTC is 6:36 in the morning, and 0004 UTC, if we're going to back up 5 hours, is 7 p.m., 7:04 p.m. local time in Evansville. Okay, that makes some measure of sense. When I got that far, I actually had originally made mistakes when I was doing this calculation, and I had to check it, but when I eventually did get these answers right, this makes some measure of sense. September 10th is close to the equinox, which is on September 21st, so we would expect the sunrise and sunset to be about 12 hours apart. On the other hand, September 10th is before, it's on the summer side of the equinox, so we would expect it to be a little longer than 12 hours of daylight, and you can see the distance, the time between sunrise and sunset is a little longer than 12 hours, it's like 12 hours and 20 minutes. Okay, that made some measure of sense, and I actually went to wolframalpha.com and I just did a search on sunrise in Evansville on September 10th, and I got 6:29 a.m. Central Daylight Time. Okay, it's not exactly the same, I'm off by 7 minutes, but I don't exactly know what they're using as the longitude of Evansville, and there's the so-called equation of time that actually corrects, I mean, we have some approximations on here and so on, but I'm happy, I got pretty close here. In the same sort of way I did the Wolfram Alpha search on sunset in Evansville on September 10th, and I got 7:07 p.m., which is pretty darn close to my answer, which was 7:04. So I guess it worked. Again, there are slight, we have a number of approximations here and so on, and who knows what approximations Wolfram Alpha is using. But you know what? We came up with some pretty good answers here. This is pretty darn close. So now we have a way to compute the elevation. On any day of the year, so like you have a solar declination, any time of the day, I could compute the elevation of the sun. The elevation, how high it is above the horizon. And in meteorology, that might be all we ever need. In an energy context, though, where we also need to know the azimuth angle here, we have to have a slightly different set of equations here. Now, azimuth, the angle that we are from north, is going to be notated as phi s. In order to compute phi s, though, you have to have this rather awkward variable h. H is called the hour angle, and it takes a little bit of explaining to see what hour angle is. Picture this path the sun follows through the sky over the course of a day. Now, at some point it'll be at local noon, or solar noon. Solar noon is a better choice of words here. Solar noon is going to be that time when the sun angle was as high in the sky as it was going to get. We're going to call that our local noon, and assign that the value h is equal to 0. Okay, so our hour angle at local noon is equal to 0. Now, picture as that sun went through the sky, hit the horizon, and it's actually, continuing a path. It's just you can't see it because it's below the horizon. Think of this as like a big unit circle, where 0 is the direction of noon, and the path it follows around the sky, like as being kind of a big unit circle here. Where like at sunset, it would be 90 degrees past that angle of 0, like at pi over 2. And at midnight, it's actually 180 degrees from where it was when it was at local noon. We'll call that pi, right, like we would on a unit circle. And actually, you go the other direction towards sunrise, and that would be a negative 90 degrees, or that would be a negative pi over 2. So we kind of are describing that path the sun turned around in the sky as, admittedly half of it being below the horizon, as being a big unit circle, with 0 being the direction of solar noon. That's what hour angle is. It's a little hard to picture, but once you have the idea in your head, it's not such a big deal to be able to think through and make sure that this is working out. And it turns out there's a fairly simple mathematical expression for it. This hour angle is just pi times the time since noon in hours divided by 12 hours. Or if you're using different units, if you're expressing the time since noon in seconds, then make sure instead of 12 hours, you have 12 hours in seconds there. Now, keep in mind that before noon, your hour angle will be negative, because you're going to have, time since noon is actually going to be a negative number, right? 1 hour before noon, your hour angle will be a negative number. 1 hour after noon, your hour angle will be a positive number there. Once you have that h, that hour angle, though, the rest of this equation for azimuth is not that complicated. Again, the left-hand side is actually a trig function of azimuth. It's cosine of phi s. And then there's all this big mess on the right side. So once again, there's going to be an inverse cosine this time in it. You're going to compute the right-hand side of this equation, and then have to take the inverse cosine of all of that to compute the actual azimuth angle. And again, notice that azimuth angle depends on your latitude and your solar declination. See, there's a delta S in there, so therefore you need the solar declination, which means you need to know the day of the year it is, and you also have this hour angle that is in there. So you compute the right-hand side and then take the inverse cosine. But there turns out to be a trick. Again, there's going to be two possible answers. What's going to happen here is this: if h turns out to be a positive number, the answer you get, you want to take 2 pi minus that answer. Okay? Mathematically, that little expression I have there at the bottom of the side is not possible, but you know what I mean. I illustrated to you that in Octave the last module, right? You're going to get a number that doesn't make a lot of sense at first, but if you take 2 pi minus that number, then you'll see, like if you make a graph of the azimuth angle with respect to time, you'll see that it makes good sense. Anytime h is greater than 0, you're just going to make your azimuth angle 2 pi minus what you got originally from this. It's a mess. It's a lot of trig. When you start making this part of your program that you're writing in Octave for Project 1, don't just sort of pound it all out and assume it works. I'll have a later video that actually helps you walk through the strategies of how to do Project 1. But, test it. Compute the elevation angles for different times and see if they make sense. Gee, wait a minute, my sun just rose. The sun rose and I got an azimuth angle of 180 degrees. Well, an azimuth angle of 180 degrees is south. Should the sun have risen in the south? or you solved for whatever. Test it. Make graphs of it. I'll show you when I give you a video that illustrates how to be testing these ideas and so on, how to actually walk through and come up with, make sure your answers are working before you move on to the next step. Now, before we move on to the next step, I do have a couple of questions for you. This is, again, just continuing the question numbering throughout this module this time. Question 6. Geometric sunrise. At geometric sunrise, the local elevation of the sun is 0 degrees, 90 degrees, or is this a trick question? Does it actually, we can't answer this question because the elevation angle of the sun at geometric sunrise varies by latitude? Or is it a trick question because actually the local elevation angle of the sun varies at sunrise with respect to the day of the year? I love questions that are multiple choice but have a trick question option there where this isn't answerable. And I love it even better when there's multiple questions that are trick question. Right? Where what is the reason you can't answer this? Or is it one of those first two choices? Make your choice from the 4 options below and get some feedback before you move on to question 7.